The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Great. So last week, or last few lectures, you heard about parallel architectures, and it started with lecture 4 on discussions of concurrency. How do you take applications or independent actors that want to operate on the same data and make them run safely together? And so just recapping the last 2 lectures, you saw really 2 primary classes of architectures, although Samad talked about a few more. There was the class of shared memory processors, the multi-cores that Intel and AMD and PowerPC, for example, have today, where you have one copy of the data, and that's really shared among all the different processors because they essentially share the same memory. And you have things like, or you need things like atomicity and synchronization to be able to make sure that the sharing is done properly so that you don't get into data race situations where multiple processors try to update the same data element and you end up with erroneous results. You also heard about distributed memory processors. So an example of that might be the cell, loosely said, where you have cores that primarily access their own local memory. And if they, while you can have a single global memory address space, to get data from memory, you essentially have to communicate with the different processors to explicitly fetch data in and out. So things like data distribution, where the data is, and what your communication pattern is like affect your performance. So what I'm going to talk about in today's lecture is programming these 2 different kinds of architectures, shared memory processors and distributed memory processors, and present you with some concepts for commonly programming these machines. So in shared memory processors, you have, say, n processors, 1 to n, and they're connected to a single memory. And if one processor asks for the value stored at address x, everybody knows where it'll go look, because there's only one address x. And so you can communicate, so different processors can communicate through shared variables, and you need things like locking, as I mentioned, to avoid race conditions or erroneous computation. So an example of parallelization, straightforward parallelization in a shared memory machine would be you have this simple loop that's just running through an array, and you're adding elements of array A to elements of array B. And you're going to write them to some new array C. Well, if I gave you this loop, you can probably recognize that there's really no data dependencies here. I can split up this loop into 3 chunks. Let's say I have 3 processors, where one processor does all the computations for iterations 0 through 3, so the first 4 iterations. Second processor does the next 4 iterations, and the third processor does the last 4 iterations. And so that's shown with the little, should probably laser pointer. So that's shown here. And what you might need to do is some mechanism to essentially tell the different processors, here's the code that you need to run, and maybe where to start. And then you may need some way of sort of synchronizing these different processors that say, I'm done, I can move on to the next computation steps. So this is an example of a data parallel computation. The loop has no real dependencies, and each processor can operate on different data sets. And what you can do is you can have a process, this is a single application, that forks off or creates what are commonly called as threads. And each thread goes on, executes, in this case, the same computation. So a single process can create multiple concurrent threads. And really, each thread is just a mechanism for encapsulating some trace of execution, some execution path. So in this case, you're essentially encapsulating this particular loop here. And maybe you parameterize your start index and your ending index, or maybe your iteration bounds, your loop bounds. And in a shared memory processor, since you're communicating, since there's only a single memory, really you don't need to do anything special about the data in this particular example, because everybody knows where to go look for it, everybody can access it, everything's independent, there's no real issues with races or deadlocks. So I just wrote down some actual code for that loop that parallelize it using p-threads, commonly used threading mechanism. Just to give you a little bit flavor for the complexity of the simple loop that we had expands to a lot more code in this case. So you have your array. It has 12 elements, A, B, and C. And you have the basic function. So this is the actual code or computation that we want to carry out. And what I've done here is I've parameterized where you're essentially starting in the array. So you get this parameter, and then you calculate 4 iterations worth. And this is essentially the computation that we're carrying out. And now in my main program, or in my main function rather, what I do is I have this concept of threads that I'm going to create. In this case, I'm going to create 3 of them. There are some parameters that I have to pass in, so some attributes, which I'm not going to get into here. But then I pass in the function pointer. This is essentially a mechanism that says, once I've created this thread, I'll go to this function and execute this particular code. And then some arguments to the function. So here I'm just passing in the index at which each loop should start with. And after I've created each thread, here implicitly in the thread creation, the code can just immediately start running. And then once all the threads have started running, I can essentially just exit the program because I've completed. So what I've shown you was that first example was a concept of, or an example of data parallelism. So you perform the same computation, but instead of operating on one big chunk of data, I've partitioned the data into smaller chunks. And I've passed it on to, I've replicated the computation so that I can get that kind of parallelism. But there's another form of parallelism called control parallelism, which essentially uses the same model of threading, but doesn't necessarily have to run the same function or run the same computation in each thread. So I've sort of illustrated that in the illustration there, where these are your data parallel computations, and these are some other computations in your code. Okay. So there's sort of a programming model that allows you to do this kind of parallelism and tries to sort of help the programmer by taking their sequential code and then adding annotations that say this loop is data parallel, or this set of code has this kind of control parallelism in it. So you start with your parallel code. This is the same program, multiple data kind of parallelization. So you might have seen in the previous talk and the previous lecture, there was SIMD, single instruction or same instruction, multiple data, which allowed you to execute the same operation, an add over multiple data elements. So here it's a similar kind of terminology. There's the same program, multiple data, and multiple programs, multiple data. This talk is largely focused on the SPMD model, where you essentially have one central decision maker, or you're trying to solve one central computation. And you're trying to parallelize that over your architecture to get the best performance. So you start off with your program, and then you annotate the code with what's parallel and what's not parallel. And you might add in some synchronization directives so that if you do, in fact, have sharing, you might want to use the right locking mechanism to guarantee safety. Now, in OpenMP, there are some limitations as to what it can do. So it in fact assumes that the programmer knows what he's doing. And the programmer is largely responsible for getting the synchronization right, or that if they're sharing, that they get those dependencies protected correctly. So you can take your program, insert these annotations, and then you go on and test and debug. So a simple OpenMP example, again using the simple loop. Now I've thrown away some of the extra code. You add in these 2 extra pragmas in this case. The first one, the parallel pragma, I call the data parallel pragma, really says that you can execute as many of the following code, or the following code block, as there are processors, or as many as you have thread context. So in this case, I've implicitly made the assumption that I have 3 processors, so you can automatically partition my code into 3 sets. And this transformation can sort of be done automatically by the compiler. And then there's a for pragma that says this loop is parallel, and you can divide up the work in a mechanism that's work sharing. So multiple threads can collaborate to solve the same computation, but each one does a smaller amount of work. So this is in contrast to what I'm going to focus on a lot more in the rest of the talk, which is distributed memory processors and programming for distributed memories. And this will feel a lot more like programming for the cell as you get more and more involved in that and your projects get more intense. So in distributed memory processor, to recap the previous lectures, you have n processors. Each processor has its own memory, and they essentially share the interconnection network. So you have each processor has its own address x. So when a processor P1 asks for x, it knows where to go look. It's going to look in its own local memory. So if all processors are asking for the same address or for the same value that's stored at address x, each one goes and looks in a different place. So there are n places to look, really. And what's stored in those addresses will vary because it's everybody's local memory. So if one processor, say P1, wants to look at the value stored in processor 2's address, it actually has to explicitly request it. The processor 2 has to send it data, and processor 1 has to figure out what to do with that copy. So it has to store it somewhere. So this message passing really uses or exposes explicit communication to exchange data. And you'll see that there's different kinds of data communications, but really the concept of what you exchange has three different, or four different rather, things you need to address. One is, how is the data described and what does it describe? How are the processes identified? So how do I identify that processor 1 is sending me this data? And if I'm receiving data, how do I know who I'm receiving it from? Are all messages the same? Well, if I send a message to somebody, do I have any guarantees that it's received or not? And what does it mean for a send operation or a receive operation to be completed? Is there some sort of acknowledgement process? So an example of a message passing program, and if you've started to look at the lab, you'll see that this is essentially this is where the lab came from, or the two, it's the same idea. I've created, here I have some two-dimensional space, and I have points in this two-dimensional space. I have points B, which are these blue circles, and I have points A, which I've represented as these yellow or golden squares. And what I want to do is, for every point in A, I want to calculate the distance to all other points B. So there's sort of a pairwise interaction between the two arrays. So a simple loop that essentially does this, there are n-squared n-squared interactions. You have a loop that loops over all the A elements, a loop that loops over all the B elements, and you essentially calculate, in this case, Euclidean distance, which I'm not showing. And you store that into some new array. So if I give you two processors to do this work, processor 1 and processor 2, and I give you some mechanism to share between the two. So here's my CPU. Here's each processor's local memory. What would be some approach for actually parallelizing this? Anybody look at the lab yet? OK, so what would you do with two processors? Right, so you split, so what was said is that you split one of the arrays in two, and you can actually get that kind of concurrency. So let's say processor 1 already has the data, and it has some place that it's already allocated where it's going to write C, the results of the computation. Then I can break up the work just like it was suggested. So what P1 has to do is send data to P2 that says, here's the data, here's the computation, go ahead and help me out. So I send the first array elements, and then I send half of the other elements that I want the calculations done for. And then P1 and P2 can now sort of start computing in parallel. But notice that P2 has its own array that it's going to store results in. And so as these compute, they actually fill in different logical places or logical parts of the overall matrix. So what has to be done is at the end, for P1 to have all the results, P2 has to send it sort of the rest of the matrix to complete it. And so now P1 has all the results, the computation is done, and you can move on. Does that make sense? OK, so you'll get to actually do this as part of your labs. So in this example messaging program, we started out with a sequential code, and we had two processors. So processor 1 actually sends the code. So this is essentially a template for the code you'll end up writing. And it does have to work in the outer loop. So this n array over which it was iterating the A array, it's only doing half as many. And processor 2 has to actually receive the data, and it specifies where to receive the data into. So I've omitted some things, for example, as to, or extra information sort of hidden in these parameters. So here you're sending all of A, all of B, whereas you could have specified extra parameters that says, I'm sending you A, here's n elements to read from A, here's B, here's n by 2 elements to read from B, and so on. But the computation is essentially the same, except for the index at which you start. In this case, I've changed for processor 2. And now, when the computation is done, this guy essentially waits until the data is received. Processor 2 eventually sends it that data, and now you can move on. Yeah?
So, would processor 2 have to wait for the data from processor 1?
Yeah, so there's I'll get into that later. So this receive, what does it mean to receive? Can I, to do this computation, I actually need this instruction to complete. So what does it mean for that instruction to complete? I do have to get the data because otherwise I don't know what to compute on. So there's some synchronization, implicit synchronization that you have to do. And in some cases, it's explicit. So I'll get into that a little bit later. Does that sort of hint at the answer? Or are you still confused?
So processor 1 doesn't do the computation, but it still sends the data to processor.
So in terms of tracing, right? Processor 1 sends the data and then can immediately start executing its code, right? Processor 2 has to wait until, in this particular example, has to wait until it receives the data. So once this receive completes, then you can actually go and start executing the rest of the code, right? So imagine that there's essentially says, wait until I have data, wait until I have something to do. Does that help?
Can the main processor send the data to both?
Can the main processor?
I mean, in cell, it's not, everybody is not peer, there's a master there.
Right.
And what master can do it, instead of doing computation, master can be the basically the quarterback, sending data, receiving data, and SPs can be basically waiting for data, get the compute, send it back. So in some sense, in cell, you probably don't want to do the computation on the master, because that means the master slows down, the master will do only the data management. So that might be one way of doing that. It's not symmetric, everything is not symmetric here.
Yep, and you'll see that in the example, because the PPE in that case has to send the data to do different SPEs. Yep.
In some sense, parts of this, the second, at least the receive part seems to be, at points seems to be inconvenient in the sense that so let's say that you have a huge array and you want to start computing before you receive the whole array, then you have to do the explicitly pipeline everything, whereas...
Yeah, we'll get into that later. Yep. Yeah, I mean, that's a good point. Communication is not cheap. And if you sort of don't take that into consideration, you end up paying a lot for the overhead for parallelizing things. Well, you can do things in software as well. We'll get into that. OK, so some crude performance analysis. So I have to calculate this distance, and given 2 processors, I can effectively get a 2x speed up. By dividing up the work, I can get done in half the time. Well, if you gave me 4 processors, I can maybe get done 4 times as fast. And in my communication model here, I have one copy of one array that's I'm essentially sending to every processor. And there's some subset of A, so I'm partitioning my other array into smaller subsets, and I'm sending those to each of the different processors. So we'll get into terminology for how to actually name these communications later. But really the thing to take away here is that this granularity, how I'm partitioning A, affects my performance and communication almost directly. And the comment that was just made is that what do you do about communication? It's not free. So all of those will be addressed. So to understand performance, we sort of summarized 3 main concepts that you essentially need to understand. One is coverage, or in other words, how much parallelism do I actually have in my application? So, and this can actually affect how much work is it worth spending on this particular application. Granularity, how do you partition your data among your different processors so that you can keep communication down, so you can keep synchronization down, and so on. Locality. So while not shown in the particular example, if 2 processors are communicating, if they are close in space or far in space, or if the communication between two processors is far cheaper than two other processors, can I exploit that in some way? And so we'll talk about that as well. So an example of sort of parallelism in an application, there are two essentially projects that are doing ray tracing, so I thought I'd have this slide here. How much parallelism do you have in a ray tracing program? In trace tracing, what you do is you essentially have some camera sources, some observer, and you're trying to figure out how to color or how to shade different pixels in your screen. So what you do is you shoot rays from a particular source through your plane, and then you see how the rays bounce off of other objects, and that allows you to render scenes in various ways. So you have different kinds of parallelisms. You have your sort of primary ray that's shot in, and if you're shooting into something like water or some very reflective surface, or some surface that can actually reflect, transmit, and you can essentially end up with a lot more rays that are created at runtime, right? So there's dynamic parallelism in this particular example. And you can shoot a lot of rays from here, so there's different kinds of parallelism you can exploit. But not all programs have this kind of sort of a lot of parallelism or embarrassingly parallel computation. There, you saw some basic code sequences in earlier lectures. So there's a sequential part, and the reason this is sequential is because there are data flow dependencies between each of the different computations. So here I calculate A, but I need the result of A to do this instruction. I calculate D here, and I need that result to calculate E. But then this loop really here is just assigning or initializing some big array, and I can really do that in parallel. So I have sequential parts and parallel parts. So how does that affect my overall speedups? And so there's this law, which is really a demonstration of diminishing returns, Amdahl's law. It says that if you have a really fast car, it's only as good as to you as fast as you can drive it. So if there's a lot of congestion on your road, or there are posted speed limits, or some other mechanisms, you really can't exploit all the speed of your car. Or in other words, you're only as fast as the fastest mechanisms of computation that you can have. So to look at this in sort of more detail, your potential speed up is really proportional to the fraction of the code that can be parallelized. So if I have some computation, let's say it has 3 parts, a sequential part that takes 25 seconds, a parallel part that takes 50 seconds, and a sequential part that runs 25 seconds. So the total execution time is 100 seconds. And if I have one processor, that's really all I can do. But if you give me more than one processor, so let's say I have 5 processors, well, I can't do anything about the sequential work. So that's still going to take 25 seconds. And I can't do anything about this sequential work either. That still takes 25 seconds. But this parallel part I can essentially break up among the different processors, so 5 in this case. And that gets me 5-way parallelism. So the 50 seconds now is reduced to 10 seconds. Is that clear so far? So the overall running time in that case is 60 seconds. So what would be my speed up? Well, you calculate speed up, old running time divided by the new running time. So 100 seconds divided by 60 seconds, or my parallel version is 1.67 times faster. So this is great. If I increase the number of processors, then I should be able to get more and more parallelism. But it also means that there's a sort of an upper bound on how much speed up you can get. So if you look at the fraction of work in your application that's parallel, and that's P, and your number of processors, well, your speed up is, let's say the old running time is just 1 unit of work. It's the time it takes for the sequential work, so it's 1 minus P, since P is the fraction of the parallel work. And it's the time to do the parallel work. And since I can parallelize that fraction over n processors, I can sort of reduce that to really small amounts in the limit. Does that make sense so far? Okay. So the speed up can tend to 1 over 1 minus P in the limit. As I increase the number of processors, or that gets really large, that's essentially my upper bound on how fast programs can work. How much can I exploit out of my program? So this is great. What this law says, the implication here is, if your program has a lot of inherent parallelism, you can do really well. But if your program doesn't have any parallelism, well, there's really nothing you can do. So parallel architectures won't really help you. And there's some interesting trade-offs, for example, that you might consider if you're designing a chip, or if you're looking at an application or domain of applications, figuring out what is the best architecture to run them on. So in terms of performance scalability, as I increase the number of processors, I have speed up. You can define sort of an efficiency to be linear at 100%, but typically you end up in sort of the sublinear domain. That's because communication is not often free. But you can get superlinear speedups on real architectures because of secondary and tertiary effects that come from register allocation or caching effects. So they can hide a lot of latency, or they can really, you can take advantage of a lot of pipelining mechanisms in the architecture to get superlinear speedups. So you can end up in really in two different domains. Okay, so a small overview of the extent of parallelism in your program and how that affects your overall execution. And the other concept is granularity. So given that I have this much parallelism, how do I exploit it? So there are different ways of exploiting it, and that comes down to, well, how do I subdivide my problem? What is the granularity of the subproblems I'm going to calculate on? And really, granularity, from my perspective, is just a qualitative measure of what is the ratio of your computation to your communication. So if you're doing a lot of computation, very little communication, you could be doing really well. Or vice versa, then you could be computation limited, and so you need a lot of bandwidth, for example, in your architecture. Yeah.
Like before, you really didn't have to give every single processor a copy of an entire copy of B.
Right.
Yeah.
Yeah. Good point. So, and as you saw in the previous slides, you have computation stages are separated by communication stages. And the communication, in a lot of cases, essentially serves as synchronization. I need everybody to get to the same point before I can move on logically in my computation. So there are two kinds of sort of classes of granularity. There's fine-grained and, as you'll see, coarse-grained. So in fine-grained parallelism, you have low computation to communication ratio. And that has good properties in that you have a small amount of work done between communication stages. Sorry, it has bad properties in that it gives you less performance opportunity. Wait, is that? It should be more, right? More opportunity for performance. Sorry, yeah, sorry. I didn't get enough sleep. Just-in-time slide creation. So less opportunities for performance enhancement, but you have a high communication ratio because essentially you're communicating very often. So these are the computations here, and these yellow bars are the synchronization points. So I have to distribute data or communicate. I do computations, but computation doesn't last very long, and I do more communication or more synchronization, and I repeat the process. So naturally, you can adjust this granularity to sort of reduce the communication overhead.
I want to actually, there's two things in that overhead part. One is the volume, so it's the amount of communication. Also, there's a large part of synchronization cost. Basically, to get a communication going, you have to go start the messages, and you have to wait till everybody's done. So that overhead also can go, even if you don't send that much data. Just the fact that you are communicating, that means you have to do a lot of this additional bookkeeping stuff that especially in a distributed memory machine is pretty expensive.
Yeah, thanks. Okay, so in coarse-grained parallelism, you sort of make the work chunks more and more so that you do the communication and synchronization less and less. And so that's shown here. You do longer pieces of work and have fewer synchronization stages. And so in that regime, you can have more opportunities for performance improvements, but the tricky thing that you get into is what's called load balancing. So if each of these different computations take differing amounts of time to complete, then what you might end up doing is a lot of people might end up idle as they wait until everybody's essentially reached their finish line. Yeah.
If you don't have to acknowledge that something's done, can't you just say, okay, I'm done with the result, hand it to the initial processor and keep doing whatever?
So you can do that in cases where that essentially there is a mechanism, or the application allows for it. But as I'll show, well, you won't see until the next lecture, there are dependencies, for example, that might preclude you from doing that. If everybody needs to reach the same point because you're updating a large data structure before you can go on, then you might not be able to do that. So think of doing molecular dynamics simulations. You need everybody to calculate a new position before you can go on and calculate new kinds of force interactions.
There's nothing else to calculate yet.
Right.
But also there's pipelining. So what we'll talk about is because you might want to get the next data while you're computing now. So when I'm done, I can start sending. So he's going to get back to us. So you can overlap some of that.
Yep. Yeah, because communication is such an intensive part, there are different ways of dealing with it, and that'll be right after load balancing. So the load balancing problem is just an illustration, and things that appear in sort of this lightish pink will serve as sort of visual cues. This is the same color coding scheme that David's using in the recitations. So this is PPU code. Things that appear in yellow will be SPU code. And these are just meant to essentially show you how you might do things like this on cell, just to help you along in picking up more of the syntax and functionality you need for your programs. So in the load balancing problem, you essentially have, let's say, three different threads of computation, and so that's shown here, red, blue, and orange. And you've reached some communication stage. So the PPU program in this case is saying, send a message to each of my SPEs, to each of my different processors, that you're ready to start. And so now, once every processor gets that message, they can start computing, and let's assume they have data and so on ready to go. And what's going to happen is each processor is going to run through the computation at different rates. This could be because one processor is faster than another, or it could be because one processor is more loaded than another, or it could be just because each processor is assigned sort of differing amounts of work. So one has a short loop, one has a longer loop. And so as the animation shows, sort of execution proceeds, and everybody's waiting until the orange guy has completed. But nobody could have made progress until everybody's reached synchronization point, because there's a strict dependence that's being enforced here that says, I'm going to wait until everybody's told me they're done before I go on to the next step of computation. And so that's, in Cell, you do that using mailboxes in this case. Is that clear so far? Okay. So how do you get around this load balancing problem? Well, there are two different ways. There's static load balancing. I know my application really, really well, and I understand sort of different computations. So what I can do is I can divide up the work and have a static mapping of the work to my processors. And static mapping just means, in this particular example, that I'm going to assign the work to different processors, and that's what the processors will do. Work can't shift around between processors. And so in this case, I have a work queue. Each of those bars is some computation. I can assign some chunk to P1, processor 1, some chunk to processor 2, and then computation can go on. Those allocations don't change. So this works well if I understand the application well, I know what the computation, and my cores are relatively homogeneous, and there's not a lot of contention for them. So if all the cores are the same, each core has an equal amount of work, total amount of work, this works really well because nobody's sitting too idle. Doesn't work so well for heterogeneous architectures or multi-cores, because one might be faster than the other. It increases the complexity of the allocation I need to do. If there's a lot of contention for some resources, then that can affect the static load balancing. So work distribution might end up being uneven. So the alternative is dynamic load balancing, and you certainly could do a sort of a hybrid load balancing, static plus dynamic mechanism, although I don't have that in the slides. So in the dynamic load balancing scheme, two different mechanisms I'm going to illustrate. So in the first scheme, you start with something like the static mechanism. So I have some work going to processor 1, and I have some work going to processor 2. But then as processor 2 executes and completes, say, fast in processor 1, some of the work, it takes on some of the additional work from processor 1. So the work that was here is now shifted. And so you can keep helping out your other processors to compute things faster. In the other scheme, you have a work queue where you essentially are distributing work on the fly. So as things complete, you're just sending them more work to do. So in this animation, I start off, I send work to different processors. P2 is really fast, so it's just zipping through things. And then P1 eventually finishes, and new work is allocated to the two different schemes. So dynamic load balancing is just intended to sort of give equal amounts of work in a different scheme for processors, so you really increase utilization and spend less and less time being idle. Okay, so load balancing was one part of sort of how granularity can have a performance trade-off. The other is synchronization. So there were already some good questions as to, well, how does this play into overall execution? When can I wait? When can't I wait? So I'm going to illustrate it with just a simple data dependence graph, although you can imagine that in each one of these circles, there's some really heavy load computation. And you'll see that in the next lecture, in fact. So if I have some simple computation here, I have some operands. I'm doing an addition. Here I do another addition. I need both of these results before I can do this multiplication. Here I have some loop that's adding through some array elements. I need all those results before I do final subtraction and produce my final result. So what are some synchronization points here? Well, really depends on how I allocate these different instructions to processors. So if I have an allocation that just says, well, let's put all these chains on one processor, put these two chains on two different processors, well, where are my synchronization points? Well, it depends on where this guy is and where this guy is. Because for this instruction to execute, it needs to receive data from P1 and P2. So if P1 and P2 are different from what's in that box, somebody has to wait. So there's a synchronization that has to happen. So I can get rid of that synchronization. So essentially, at all join points, there's potential for synchronization. But I can adjust the granularity so that I can remove more and more synchronization points. And so, whoops, screw up in the animation. So if I had assigned all this, this entire subgraph to the same processor, I really get rid of the synchronization because it's essentially local to that particular processor. And there's no extra messaging that has to happen across processors that says, I'm ready, or I'm ready to send you data, or you can move on to the next step. And so in this case, the last synchronization point would be at this join point. Let's say if it's allocated on P1 or on some other processor. So how would I get rid of this synchronization point? Right, you put the entire thing on a single processor, but you get no parallelism in this case. Right? So the coarse grain, fine grain parallelism granularity issue comes to play. So the last sort of thing I'm going to talk about in terms of how granularity impacts performance, and this was already touched on, is that communication is really not cheap and can be quite overwhelming on a lot of architectures. And what's interesting about multicores is that they're essentially putting a lot more resources closer together on a chip. So essentially changing the factors for communication. So rather than having your parallel cluster now, which is connected, say, by Ethernet or some other high-speed link, now you essentially have large clusters, or will have large clusters on a chip. So communication factors really change. But the cost model is relatively captured by these different parameters. So what does it actually take me, or what is the cost of my communication? Well, it's equal to, well, how many messages am I sending, and what is the frequency with which I'm sending them? There's some overhead for a message. So I have to actually package data together. I have to stick in a control header and then send it out. So that takes me some work on the receiver side. I have to take the message. Maybe I have to decode the header, figure out where to store things, where to store the data that's coming in on the message. So there's some overhead associated with that as well. There's a network delay for sending the message, so putting a message on the network so that it can be transmitted, or picking things up off the network. So there's a latency also associated with how long does it take for a message to get from point A to point B. What is the bandwidth that I have across a link? So if I have a lot of bandwidth, then that can really lower my communication costs. But if I have little bandwidth, then that can really create contention. How much data am I sending? And number of messages. So this numerator here is really an average of the data you're sending per communication. There's a cost induced per contention. And then finally, so all of these are additive factors. The higher they are, except for bandwidth, because it's in the denominator here, the worse your communication cost becomes. So you can try to reduce the communication cost by communicating less. So you adjust your granularity, and that can impact your synchronization or what kind of data you're shipping around. You can do some architectural tweaks or maybe some software tweaks to really get the network latency down and the overhead per message down. So on something like the raw architecture, which you saw in Saman's lecture, there's a really fast mechanism to communicate nearest neighbor in 3 cycles. So one processor can send a single operand to another reasonably fast. You can improve the bandwidth, so again, an architectural mechanism. You can do some tricks as to how you package your data in each message. And lastly, what I'm going to talk about in a couple of slides is, well, I can also improve it using some mechanisms that try to increase the overlap between messages. And what does this really mean? What am I overlapping it with? And it's really the communication and computation stages are going to somehow get aligned. So before I can show you that, I just want to point out that there are 2 kinds of messages. Right? There's data messages, and these are, for example, the arrays that I'm sending around to different processors for that distance calculations between points in space. But there are also control messages. So control messages essentially say, I'm done, or I'm ready to go, or is there any work for me to do? So on cell, control messages, you can think of using mailboxes for those, and the DMAs for doing the data communication. So data messages are relatively much larger. You're sending a lot of data versus control messages that are really much shorter. Just essentially, just sending you very brief information. Okay, so in order to get that overlap, what you can do is essentially use this concept of pipelining. So you've seen pipelining in superscalar. Someone talked about that. And what you're essentially trying to do is break up the communication and computation into different stages, and then figure out a way to overlap them so that you can essentially hide the latency for the sends and receives. So let's say you have some work that you're doing and really requires you to send the data or get it. Somebody has to send you the data, or you essentially have to wait until you get it. And then after you've waited and the data is there, you can actually go on and do your work. So these are color-coded, so this is essentially one iteration of the work. And so you can overlap them by breaking up the work into send, wait, work stages, where each iteration, I'm trying to send or request the data for the next iteration. I wait on the data from a previous iteration, and then I do my work. So depending on how I partition, I can really get really good overlap. And so what you want to get to is the concept of a steady state, where in your main loop body, all you're doing is essentially prefetching or requesting data that's going to be used in future iterations for future work. And then you're waiting on, yeah, I think my color coding is a little bit bogus. That's good. Okay, so here's an example of how you might do this kind of buffer pipelining in cell. So I have some main loop that's going to do some work that's encapsulated in this process data. And what I'm going to use is 2 buffers. So this scheme is also called double buffering. I'm going to use this ID to represent which buffer I'm going to use. So it's either buffer 0 or buffer 1. And this instruction here essentially flips the bit. So it's either 0 or 1. So I fetch data into buffer 0, and then I enter my loop. So this is essentially the first send, which is trying to get me 1 iteration ahead. So I enter this main loop, and I do some calculation to figure out where to write the next data, and then I do another request for the next data item that I'm going to, sorry, there's an M missing here, just noticed it. I'm going to fetch data into a different buffer, right? This is ID, where I've already flipped a bit once. So this get is going to write data into buffer 0, and this get is going to write data into buffer 1. I flipped a bit again, so now I'm going to issue a wait instruction that says, has the data from buffer 0, is the data from buffer 0 ready? And if it is, then I can go on and actually do my work. Does that make sense? People confused? Should I go over it again? OK. So this is an XOR. So I could have just said buffer equals 0 or buffer equals 1. Oh, sorry, this is 1, yeah. So this is a 1 here, and an M. last minute editing. Did that confuse you?
But like, I don't see the
Okay, so I'll go over it again. So this get here is going to write into ID 0. So that's buffer 0, right? And then I'm going to change the ID. So imagine there's a 1 here. So now the next time I use ID, which is here, I'm trying to get the data, and I'm going to write it to buffer 1. The DMA on the cell processor essentially says I can send this request off, and I can check later to see when that data is available. But that data is going to go into a different buffer, essentially B1, whereas I'm going to work on buffer 0, right, because I changed the ID back here. Now do you get it? So I fetch data into buffer 0 initially before I start the loop, and then I start working. I probably should have had an animation in here. So then you go into your main loop. You try to start fetching into buffer 1, and then you try to compute out of buffer 0. But before you can start computing out of buffer 0, you just have to make sure that your data is there. And so that's what the synchronization is doing here. Hope that was clear. OK, so this kind of computation and communication overlap really helps in hiding the latency. And it can be really useful in terms of improving performance. And there are different kinds of communication patterns. So there's point-to-point, and you can use these both for data communication or control communication. And it just means that one processor can explicitly send a message to another processor. There's also broadcast that says, hey, I have some data everybody's interested in, so I can just broadcast it to everybody on the network. Or reduce, which is the opposite. That says, everybody on the network has data that I need to compute, so everybody send me their data. There's an all-to-all, which says all processors should just do a global exchange of data that they have. And then there's a scatter and a gather. So scatter and a gather are really different types of broadcasts. So it's one to several, or one to many, and gather, which is many to one. So this is useful when you're doing computation that really is trying to pull data in together, but only from a subset of all processors. So it depends on how you've partitioned your problems. So there's a well-known sort of message passing library specification called MPI that tries to essentially implement, that tries to specify all of these different communications, and in order to sort of facilitate parallel programming. It's full-featured, actually has more types of communications and more kinds of functionality than I showed on the previous slides. But it's not a language or a compiler specification. It's really just a library that you can implement in various ways on different architectures. Again, it's a same program, multiple data, or supports the SPMD model. And it works reasonably well for parallel architectures, for clusters, heterogeneous and multi-cores, homogeneous multi-cores. Because really all it's doing is just abstracting out, well, it's giving you a mechanism to abstract out all the communication that you would need in your computation. So you can have additional things like precise buffer management. You can have some collective operations that I'll show you an example of for doing things in a scalable manner when when a lot of things need to communicate with each other. So just a brief history of where MPI came from. And very early when parallel computers started becoming more and more widespread, and there were these networks, and people had problems porting their applications or writing applications for each scheme just because it was difficult, as you might be finding in terms of programming things with the cell processor. There needed to be ways to sort of address the spectrum of communication. And it often helps to have a standard, because if everybody implements the same standard specification, then it allows your code to be ported around from one architecture to the other. And so MPI came around. The first forum was organized in 1992, and there had a lot of people participating in it, from vendors, people like IBM, companies like IBM, Intel, and people who were interested or who had expertise in writing libraries, users who were interested in using these kinds of specification to do their computations, so scientific people who were in the scientific domain, And it was finished in about 18 months. I don't know if that's a reasonably long time or short time, but considering I think the MPEG-4 standard took a bit longer to do. As a comparison point, I don't have the actual data. So point-to-point communication. And again, a reminder, this is how you would do it on cell. These are SPE sends and receives. You have one processor that's sending data to another processor. And you have some network in between. And processor A can essentially send the data explicitly to processor 2. And the message in this case would include how the data is packaged, some other information such as the length of the data, destination, possibly some tags so you can identify the actual communication. And there's a mapping, natural mapping for the actual functions on cell. There's a get for the send and a put for the receive. Well, quite. OK. So there was a question of, well, how do I know if my data actually got sent? How do I know if it was received? And there's you can think of a synchronous send and a synchronous receive, or an asynchronous communication. So in the synchronous communication, you actually wait for a notification. So this is kind of like your fax machine. You put something into your fax, it goes out, and you eventually get a beep that says your transmission is OK. Or if it wasn't OK, then you get a message that says something went wrong, and you can redo your communication. In the asynchronous send, it's kind of like you.
Most probably you can get a reply to it.
Yeah, you can get a reply. Thanks. In the asynchronous send, it's like you write a letter, you go put it in the mailbox, and you don't know whether it actually made it into the actual postman's bag and it was delivered to your destination, or if it was actually delivered. So you only know that the message was sent. You put it in the mailbox, but you don't know anything else about what happened to the message along the way. There's also the concept of a blocking versus a non-blocking message. So this is orthogonal really to synchronous versus asynchronous. So in blocking messages, a sender waits until there's some signal that says the message has been transmitted. So this is, for example, if I'm writing data into a buffer and the buffer essentially gets transmitted to somebody else, we wait until the buffer is empty. And what that means is that somebody has read it on the other end, or somebody has drained that buffer from somewhere else. The receiver, if he's waiting on data, well, he just waits. He essentially blocks until somebody has put data into the buffer. And you can get into potential deadlock situations. So you saw deadlock with locks in the concurrency talk. I'm going to show you a different kind of deadlock example. An example of a blocking send on cell allows you to use mailboxes. Or you can sort of use mailboxes for that. Mailboxes, again, are just for communicating short messages, really, not necessarily for communicating data messages. So an SPE does some work, and then it writes out a message, in this case, to notify the PPU that, let's say, it's done. And then it goes on and does more work. And then it wants to notify the PPU of something else. So in this case, this particular send will block because, let's say, the PPU hasn't drained this mailbox. It hasn't read the mailbox. So you essentially stop and wait until the PPU has caught up.
So all mailbox sends are blocking?
Yes. David says yes. Right. A non-blocking send is something that essentially allows you to send a message out and just continue on. You don't care exactly about what's happened to the message or what's going on with the receiver. So you write the data into the buffer and you just continue executing. And this really helps you in terms of avoiding idle times and deadlocks, but it might not always be the thing that you want. So an example of sort of a non-blocking send and wait on cell is using the DMAs to ship data out. You can put something, put in a request to send data out on the DMA, and you could wait for it if you want, in terms of making sure that reading the status bits to make sure it's completed. Okay, so what is the source of deadlock in the blocking case? And it really comes about if you don't really have enough buffering in your communication network. And often you can resolve that by having additional storage. So let's say I have processor 1 and processor 2, and they're trying to send messages to each other. So processor 1 sends a message. At the same time, processor 2 sends a message. And these are going to go, let's say, into the same buffer. Well, neither can make progress because somebody has to essentially drain that buffer before these receives can execute. So what happens with that code is it really depends on how much buffering you have between the two. If you have a lot of buffering, then you may never see sort of the deadlock. But if there's a lot of, if you have a really tiny buffer, then you do a send. The other person can't do the send because the buffer hasn't been drained, and so you end up with a deadlock. And so a potential solution is, well, you actually increase your buffer length, but that doesn't always work because you can still get into trouble. So what you might need to do is essentially be more diligent about how you order your sends and receives. So if you have processor 1 doing a send, make sure it's matched up with a receive on the other end. Similarly, if you're doing a receive here, make sure there's sort of a matching send on the other end. And that helps you in sort of making sure that things are operating reasonably in lockstep at partially ordered times. Okay. Broadcast mechanism. So I showed you that was really examples of point-to-point communication. A broadcast mechanism is slightly different. It says, I have data that I want to send to everybody. It could be really efficient for sending short control messages, maybe even efficient for sending data messages. So as an example, if you remember our calculation of distances between all points, the parallelization strategy said, well, I'm going to send one copy of the array A to everybody. So in the 2-processor case, that was easy. But if I have n processors, then rather than sending point-to-point communication from A to everybody else, what I could do is just say broadcast A to everybody, and they can grab it off the network. So in MPI, there's this directive, or this function MPI broadcast that does that. I'm using sort of generic abstract sends, receives, and broadcast in my examples. So you can broadcast A to everybody. And then if I have n processors, then what I might do is distribute the m's in a round-robin manner to each of the different processors. So you pointed this out. I don't have to send B to everybody. I can just send, in this case, one particular element. Is that clear? Okay.
There's no broadcast on cell?
There is no broadcast on cell. There is no mechanism for reduction either. And you can't quite do scatters and gathers, I don't think. OK, so an example of a reduction, I said it's the opposite of a broadcast. Everybody has data that needs to essentially get to the same point. So as an example, if everybody in this room had a value, and including myself, and I wanted to know what is the collective value of everybody in the room, you all have to send me your data. Now, this is important because if, in this case, we're doing an addition, it's an associative operation. So what we can do is we can be smart about how the data is sent. So guides that are close together can essentially add up their numbers and forward me. So instead of getting n messages, I can get log n messages. And so if every pair of you added your numbers and forwarded me that cuts down communication by half. And so you can, starting from the back of the room, by the time you get to me, I only get 2 messages instead of n messages. So a reduction combines data from all processors. In MPI, there's this function MPI reduce for doing that. And the collective operations are things that are associative. And, subtract, and, or, and. You can read them on slide. No processor. There's a semantic caveat here is that no processor can finish the reduction before all processors have at least sent it one data, or have contributed, rather, a particular value. So in many numerical algorithms, you can actually use the broadcast and send, the broadcast and reduce in place of sends and receives, because it really helps to improve the simplicity, or it improves the simplicity of your computation. You don't have to do n sends to communicate data. You can just broadcast. It gives you a mechanism for essentially having a shared memory abstraction on distributed memory architecture. There are things like all-to-all communication, which also help you in that sense, although I don't talk about all-to-all communication here. So I'm going to show you an example of sort of a more detailed MPI. But I also want to contrast this to the OpenMP programming on shared memory processors, because one might look simpler than the other. So suppose that you have a numerical integration method that's essentially you're going to use to calculate pi. So as you get finer and finer, you can get more accurate. As you shrink these intervals, you can get better values for pi. And the code for doing that, some C code, you have some variables, and then you have a step that essentially tells you how many times you're going to do this computation. And for each time step, you calculate this particular function here. And you add it all up, and in the end, you can sort of print out what is the value of pi that you've calculated. So clearly, as you shrink your intervals, you can get more and more accurate measures of pi. So that translates to increasing the number of steps in that particular loop, or in that particular C code. So you can compute, you can use that numerical integration to calculate pi with OpenMP. And what that translates to is, sorry, it should have been animation here. It asked you what I should add in. You have this particular loop, and this is the computation that you want to parallelize. And there's really 4 questions that you essentially have to go through. Are there variables that are shared? Because you have to get the process right. If there are variables that are shared, you have to explicitly synchronize them and use locks to protect them. What values are private? So in OpenMP, things that are private are data on the stack. Things that are defined lexically within the scope of the computation that you encapsulate by an OpenMP pragma, and what variables you might want to use for reduction. So in this case, I'm doing a summation, and this is the computation that I can parallelize. Then I essentially want to do a reduction with a plus operator, since I'm doing an addition, on this variable. This loop here is parallel. It's data parallel. I can split it up. It's the loop. The for loop is also, I can do this work sharing on it. So I use the parallel for pragma. And the variable x here is private. It's defined here, but I can essentially give a directive that says, this is private. You can essentially rename it on each processor. Its value won't have any effect on the overall computation, because each computation will have its own local copy. Is that clear so far? OK, so computing pi with integration using MPI takes up 2 slides. I could fit it on 1 slide, but you couldn't see it in the back. So there's some initialization. In fact, I think there's only 6 basic MPI commands that you need for computing. 3 of them are here, and you'll see the others are MPI send, MPI receive, and there's one more that you'll see on the next slide. So there's some loop that says, while I'm not done, keep computing. And what you do is you broadcast n to all the different processors. N is really your time step. How many small intervals of execution are you going to do? And you can go through, do your computation. So now the MPI essentially encapsulates the computation over n processors. And then you get to an MPI reduce command at some point that says, OK, what values did everybody compute? Do the reduction on that. Write that value into my MPI. Now what happens here is there's processor ID 0, which I'm going to consider the master. So he's the one who's going to actually print out the value. So the reduction essentially synchronizes until everybody's communicated a value to processor 0. And then it can print out the pi. And then you can finalize, which actually makes sure computation can exit, and you can go on and terminate. OK. So last concept in terms of understanding performance for parallelism is this notion of locality. And there's locality in your communication and locality in your computation. So what do I mean by that? So in terms of communication, if I have some 2 operations, and let's say this is a picture or schematic of what the raw chip, the MIT raw chip looks like. Each one of these is a core. There's some network, some basic computation elements. And if I have an addition that feeds into a shift, well, I can put the addition here and the shift there. But that means I have a really long path that I need to go to in terms of communicating that data value around. So the computation naturally should just be closer together, because that decreases the latency that I need to communicate. So rather than doing that mapping, what I might want to do is just go to somebody who's close to me and available.
also there a volume issue?
So assume more than that, if a lot of other people also want to communicate. So if it is randomly distributed, so you can assume there's a lot more communication going into in each channel. Whereas if you put locality in there, then you can scale communication much better than scaling the network.
There's also a notion of locality in terms of memory accesses. And these are potentially also very important, or more important rather, because of the latencies for accessing memory. So if I have this loop that's doing some addition or some computation on an array, and I distribute it, say, over 4 processors, this is, again, let's assume a data parallel loop. So what I can do is have a work sharing mechanism that says, this thread here will operate on the first 4 indices. This thread here will operate on the next 4 indices, and next 4 and the next 4. And then you essentially get to the join barrier, and then you can continue on. And if we consider how the access patterns are going to be generated for this particular loop, well, in the sequential case, I'm essentially generating them in sequence. So that allows me to exploit, for example, on traditional cache architecture, a notion of spatial locality. If I look at how things are organized in memory, in a sequential case, I can perhaps fetch an entire block at a time. So I can fetch all the elements of A0 to A3 in one shot. I can fetch all the elements of A4 to A7 in one shot. And that allows me to essentially improve performance because I overlap communication. I'm predicting that once I see a reference, I'm going to use data that's adjacent to it in space. There's also a notion of temporal locality that says if I use some particular data element, I'm going to reuse it later on. I'm not showing that here. But in the parallel case, what could happen is if each one of these threads is requesting a different data element, and let's say execution essentially proceeds, all the threads are requesting their data at the same time, then all these requests are going to end up going to the same memory bank. The first thread is requesting ace of 0. Next thread is requesting ace of 4. Next thread, ace of 8. Next thread, ace of 12. And all of these happen to be in the same memory bank. So what that means is there's a lot of contention for that one memory bank. And in effect, I've serialized the computation. Right? Everybody see that? And this can be a problem in that you can essentially fully serialize the computation in that there's contention on the first bank, contention on the second bank, and then contention on the third bank, and then contention on the fourth bank. And so I've done absolutely nothing other than pay overhead for parallelization. I've made extra work for myself in creating these threads. Maybe I've done some extra work in terms of synchronization. So I'm fully serial. So what you want to do is actually reorganize the way data is laid out in memory so that you can effectively get the benefit of parallelization. So if you have the data organized as is there, you can shuffle things around, and then you end up with a fully parallel or a layout that's more amenable to full parallelism because now each thread is going to a different bank, and that essentially gives you a 4-way parallelism. And so you get the performance benefits. So there are different kinds of considerations you need to take into account for shared memory architectures in terms of how the design affects the memory latency. So in a uniform memory access architecture, every processor is either, you can think of it as being equidistant from memory, or another way, it has the same access latency for getting data from memory. Most shared memory architectures are non-uniform, so also known as NUMA architecture. So you have physically partitioned memories, and the processors can have the same address space, but the placement of data affects the performance because going to one bank versus another can be faster or slower. So what kind of architecture is CEL? Yeah. No guesses?
It's not shared memory.
Right, it's not a shared memory architecture. OK. So summary of parallel performance factors. So there's 3 things I tried to cover. coverage of coverage or the extent of parallelism in your application. So you saw Amdahl's law, and actually gave you a sort of a model that said when is parallelizing your application going to be worthwhile. And it really boils down to how much parallelism you actually have in your particular algorithm. If your algorithm is sequential, then there's really nothing you can do for programming for performance using parallel architectures. Talked about granularity of the data partitioning and the granularity of the work distribution. If you had really fine-grained things versus really coarse-grained things, how does that translate to different communication costs? And then last thing I showed was locality. So if you have near neighbors talking that may be different than two things that are further apart in space communicating, and there's some issues in terms of the memory latency and how you actually can take advantage of that. So this really is a overview of sort of the parallel programming concepts and the performance implications. So the next lecture will be, how do I actually parallelize my program? And we'll talk about that.